Hello, we are going to talk today about Newton's law of universal gravitation. Gravitation should be here, T here. Gravitation. Okay. So, how the Newton law of universal gravitation states? So it's usually stated as that every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Any particle, if you have one here, M3, for example, there are also they attract each other. These two particles also attract each other, and so on. So there are always forces between these particles in the universe, or masses or objects. And this law, in its final form, can be written as what is that force between the two particles, for example? It's Fg, G for gravitations, equals the G constant, gravitation constant, times the mass 1 times mass 2, the two masses proportional. This law is directly proportional, or this force is directly proportional to the product of the masses and inversely proportional to the distance, to the square of the distance between them, r. And that's how it is written. So, and this constant equals a very small number, 6.67, 10 minus 11 Newton times meter square over kilogram square. Now, what I'm going to do here is to, the question is, when you have Earth, and let's say maybe Earth like this, let's say you have an apple that is falling from about 1 meter above the Earth. So let's say from here to here is about 1 meter. Now, how much this force? Of course, the Earth attract the apple with this force F. Let's say F. This is apple. This is Earth. Let's put this. The force exerted by the Earth on the apple is FEA, and the force exerted by the apple on the Earth, let's call it, so it's going to be this way, let's call it F apple Earth. Okay. And the distance between the centers of these two masses, which is the Earth, the huge mass of the Earth, and the apple, will be this distance here. So this distance, basically distance, equals radius of Earth, that's Earth radius, okay, plus the 1 meter, the distance between them. So the center of the apple is really near, it's very small compared to 1 meter. Let's just keep it 1 meter here. And knowing this information, and let's say the mass of apple, mass apple, how about mass of apple? Let's take 200 grams for one apple. I think it's correct approximation. It's valid approximation. And this give me basically 0.2 kilograms. So what I'm going to do here is, the question is, now the apple is going to fall toward the Earth. We know that, so there is no doubt about that. The problem that we have is the Earth accelerating toward the apple, is the Earth is moving toward the apple, right? So that's another question here. I'm not trying to approve or disapprove other claims, but let's see. Let's try mathematically or physically solve this kind of question. Let's say I am going to calculate the force between the apple that exerted by the earth on the apple. By the way, what's that force? That force is the weight, right? The weight of the apple, and equals m apple times the acceleration due to the gravity, right? G. Okay. And according to the law, universal gravitational law, so let's put this big G constant, apple and earth over let's put distance here instead of the r to make it clear. So let's put here distance, which is the radius of the earth plus the height of where the apple is initially positioned. Okay, so let's basically just plug the numbers. This force equals G is 6.6710 minus 11 Newton times meter square divided by kilograms square. Okay, very important to keep an eye on the unit, times ma, the mass of the apple is 0.2 kilograms, times the mass of the earth, which is mass earth 5.98, very huge, 24 kilograms. And this divided by the distance between them. Basically, the distance between them is the radius. This is equatorial radius, 6378. I'm gonna put the meter here, kilometers. So if we multiply by 10 power 3, it will be meters times here. So the square plus the height, which is 1 meter. We said the apple is 1 meter from the surface of the earth. So the total distance is the radius plus the height. Okay, you see this number 1 meter is very small compared to this one number. So basically we're just going to ignore it. And here is square. Let's calculate this, do this calculation here. So this gives me about 2 Newton. And here you can see there is meter square that can be cancelled with meter square here. Okay, let me show you just how I did how I came up to with the Newton. So meter square can be also cancelled with meter here and square. You see square here, and kilogram square can be cancelled with this 2 kilograms here, and basically we just end up with Newton. Okay, so the force exerted by the earth on the apple equals 2 Newton. Okay, and from here we can calculate how much the acceleration of the apple toward the earth, how much it accelerates the apple when it falls down, how much it accelerates. We know that the force exerted by the earth on the apple equals the weight of the apple and equals mass of the apples times the acceleration of the apple. Now, because we want to calculate this acceleration, right? So, so from here, G equals 2 Newton divided by the mass of the apple, which is 0.2 kilograms. What is the units of Newton? So 2 divided by 0.2, I think it's just 10. Equals 10. What is Newton? Newton is kilogram meter per second square over kilograms, and you can see here we got to the unit of the acceleration, which is meters per second square. Because I did some approximation here, then this also equals the known value of the acceleration due to the gravity. Okay, so this is how much the apple is accelerating toward the Earth surface, and we know that, we have seen that, we can do a lab experiment to measure that. So the other thing that I'm going, the other question is the Earth actually accelerating? If according to the law, it says it's usually stated that every particle attracts every other particle, which means the apple is actually attracting the Earth toward it. Now the question, we don't see that. Nobody sees that, right? So how we can calculate the acceleration of the Earth towards the apple? Let's see. So this is the force. So the force. Let me change here the color. So the force of Earth on apple equals actually, it's the same magnitude as the force of the apple on Earth. Okay, and equals 2 Newton. After the approximation that I made, from these calculations here, I think it's 1.96 or 97, something like that. And now, so the force of apple on Earth equals what? So it's gonna be the mass of Earth times the acceleration of the Earth toward the apple, if there is one. Okay, of course there is one, but how much? So, and this gives me, so if I want to calculate this, because we know the acceleration, we just calculate the acceleration of the apple toward the Earth. So I'm going to calculate now the acceleration of the Earth towards the apple. So A Earth equals F apple Earth, the force exerted by the apple on the Earth over the mass of the Earth. Let me now plug the numbers. AE equals 2 newtons divided by the mass of the Earth, which is, we have it already here somewhere, 5.98, 5.98, then 24 kilograms. And this gives me, if I convert Newton to kilogram meter per second square, so 2 over 5.98 kilograms meters per second square over kilograms. So I can cancel kilograms and end up with the unit of the acceleration. And this basically gives me around 2 over 5.98 times 10 minus 24 meters per second square. Now, that's the acceleration of Earth, okay? This is very, extremely small number, very small. It's almost, nothing. So that's the reason why we don't see the Earth accelerating toward the apple, even though there is an acceleration, but it's very, extremely small. Hope this helps.